Suppose we have the following system of linear equations and we want to solve for the values x1, x2, and x3 such that each of these equations will be true. One way to do that is to use a method known as LU decomposition, which is this four-step process right here. So I'm going to walk through an example of how to use these 4 steps to actually solve this system of linear equations. So the first step says we need to write the linear equations as a matrix equation AX equals B. So here's how we can do that. Okay, so matrix A, this is going to be our coefficient matrix. So notice that each of the values in this matrix are just the coefficients in the linear equations up here. Then we have the vector X, which is just x1, x2, and x3. And then we have the vector B, which is just the values on the right-hand side of each equation. So that's step 1. We've rewritten the linear equations in matrix form. Step 2 says substitute LU for A to create the equation LUX equals B. So instead of AX equals B, we're going to replace this A with an LU to form this equation, LUX equals B, where L is a lower triangular matrix and U is an upper triangular matrix. So I'm going to create a little space right here and rewrite the coefficient matrix. All right, so I've rewritten the coefficient matrix right here. What we're going to do is perform elementary row operations on this matrix to convert it to the upper triangular matrix. Now, as a reminder, the upper triangular matrix is a matrix where there's a triangle in the upper right corner of values, and all the values below the triangle, so this value, this value, this value, these are all equal to 0. So what we're going to do is perform row operations to make each of these values equal to 0. So the first step is let's make this 3 a 0. So how can we do that? Well, what we can say is row 2, so the values in row 2 are going to become, if we multiply this value in row 1 by -3, that would be -3 times 1 plus 3, that would make a 0 right here. So what we can say is -3 times row 1 plus row 2. That's what row 2 is going to become, because that's what will produce a 0 right here. So let's do that. Let's rewrite our matrix right here. So the first row won't change at all, and the last row won't change at all for this step. So let's rewrite that. So we have -3 times row 1. So -3 times 1 plus 3, that's a 0. So we get a 0 right here. And then we have -3 times 3, that's -9, plus -1 is -10. And then we have -3 times -3, that's 9, plus 4 is 13. So that's the first step towards building this upper triangular matrix. Now, what we can do is we can also build the lower triangular matrix at the same time. And the way that we do that is we just take whatever value that we had to multiply one of the rows by in this elementary row operation. So in this case, we had to multiply by a -3. We're going to take the opposite of that value, so a +3, and we're going to write it in the position of the lower triangular matrix where we just obtained the 0 in the upper triangular matrix. So we can see we just obtained this 0 in column 1, row 2. So that's why in column 1, row 2 of the lower triangular matrix, we're just going to write the opposite value of this -3. Okay, the next step is we need to make this value a 0. So we'll notice if we just do row 1 plus row 3, 1 plus a -1, that will produce a 0. So what we can say is row 3 is just going to become row 1 plus row 3. So let's write the results of that. So row 1 and row 2 won't change at all, so I'll just rewrite those. So we have row 1 plus row 3. So 1 plus a -1, that's a 0. So we have a 0 right here. Then we have 3 plus 2, that's 5. And then we have -3 plus -1, that's -4. So for our lower triangular matrix, for this position right here, we need to write the opposite sign of whatever we had to multiply by. So in this case, we didn't actually have to multiply any of the rows by anything. So another way of saying that is we could have just said we multiplied it by 1, so we didn't change it at all. So the opposite of 1 is a -1. So we'll put a -1 right here in the same position of the 0 that we just found in the upper triangular matrix. Okay, the last step is we need this 5 to become a 0. So how can we do that? Well, notice if we take half of -10, that would be -5. And if we add that to 5, that would be a 0. So let's do that. Let's say row 3 is going to become 1/2 of row 2 plus row 3. So when we do that, let's see what we get. So the first 2 rows don't change at all. So in row 3, we said we'll have half of negative 10 plus 5, that's 0. And in this last entry, we have half of 13, so let's write that right here. 13 divided by 2 plus row 3. So row 3, we have negative 4. If we want to write that as a fraction over 2, that would be minus 8 over 2. So when we add these two together, 13 minus 8 is 5, so we get 5 over 2 in this last position right here. 5 over 2. Okay, so for this last value in the lower triangular matrix right here, we're going to take the opposite of 1/2, which is negative 1/2. So now we have our lower triangular matrix, and this matrix is our upper triangular matrix. So we figured out those two, so now we can move on to step 3, which says solve Ly equals B for y. So let's write that equation right here. Okay, so here we have written the matrix equation Ly equals B, where L, this is the lower triangular matrix that we just found. Y is just a vector of y values that we've created. And B, remember B is just the values on the right-hand side of the original linear equations. So what we can do is write this as a series of linear equations, and we're going to solve for the y values. So here's what that would look like. All right, so we need to solve this system of equations for the y values. So let's start with this first equation. Y1 is 12. So that's pretty easy. We can just write y1 is equal to 12. That's our first y. Now, if we plug this y1 equal to 12 into this second equation, we get 3 times 12, that's 36. 36 plus y2 is equal to 0. y2 must be negative 36 to have a 36 plus a negative 36 equal to 0. So we'll say y2 is negative 36. And then lastly, we can plug this value of y1 and y2 into this last equation to solve for y3. So we get negative y1 is 12, so let's write that. Negative 12 minus 1/2 times y2 we said is negative 36, plus y3 is equal to 1. So negative 1/2 times negative 36, this is a positive 18. So we have negative 12 plus 18, that's 6. So really this is 6 plus y3 is equal to 1. To solve for y3, we can subtract a 6 from both sides, and we find that y3 is equal to 1 minus 6 is negative 5. So that's step 3. Step 3 is complete. We solved for y1, y2, and y3. The last step is we need to write the matrix equation ux equals y, and we're going to solve for x. So here's what that would look like. Alright, so here's the matrix equation ux equals y, where u is the upper triangular matrix that we found, x is this vector of x1, x2, and x3, and y is the vector of y values that we just found in the previous step. So let's go ahead and write this as a system of linear equations, and we're going to solve for x. So here's what that looks like. Okay, so we have this system of linear equations here, and we're just going to solve for x1, x2, and x3. So let's start with this last equation down here. Let's solve for x3. Notice that we can multiply both sides by 2 to get rid of this 2 in the denominator. So we would be left with 5 times x3 is equal to negative 5 times 2 is negative 10. To solve for x3, we can divide both sides by 5. We'll find that x3 is equal to negative 10 divided by 5 is negative 2. So there's our first answer. x3 is equal to negative 2. Next, we can plug this value into this second equation right here, and we'll solve for x2. So if we plug in a negative 2 right here, we get 13 times negative 2, that's negative 26. And then if we add a 26 to this side, negative 36 plus 26 would be negative 10. So what we'll have is negative 10x2 is equal to negative 10. And we can divide both sides by negative 10 to find that x2 is equal to negative 10 divided by negative 10 is just 1. So x2 is equal to 1. And the last step is we'll plug in x2 and x3 into this top equation right here and solve for x1. So for x3, we'll plug in a negative 2 right here. Negative 3 times negative 2, this would become a 6. So let's write that right here. And then if we plug in a 1 right here, we get 3 times 1 is 3. So let's have a 3 right there. So let's write what we have. We're running out of room, but that's okay. We have x1 plus 3 plus 6 is 9 is equal to 12. We'll see that if we subtract a 9 from each side, x1 would be equal to 3. So those are our answers. x1 is 3, x2 is 1, and x3 is negative 2. And you'll find that if you plug these three values into any of these original 3 linear equations, they will all be true. So that is how you can use LU decomposition to solve a system of linear equations.